So part of graph theory, I mean, there's a whole bunch of stuff going on with graph theory, and you have all of these edges, and we have corners, real generic talk. And what I mean by the edges and corners is I go back to something that you may have done at some point, and if I take an envelope which looks like this, can you draw that envelope without lifting your pencil? Can you draw that without lifting your pencil? And the non-mathematic person, they get ready and they go ahead and they start drawing it and coming up with a bunch of different possibilities. You know, some might come down and then go over and go up and go over and up and down. And like, oh crap, that was close. But what if I started here and went up and went down and went over, went up, woohoo. You know, I've done this enough times. I know that it actually works. Okay. So it actually does work. And some of you are trying it right now. So I'll talk slow so you can see if you can get it. But I was able to get it. Now, what if I gave you another one, you know, something like an envelope? I don't know. And maybe put another line in there somehow. Like, what if I did, you know, we have this. Clearly, I can draw that without lifting a pencil. Well, these are actually just called graphs. These graphs have a bunch of, you know, these spots, which we could call nodes. Another common name that's used is vertices. Okay, so those two go the same. And then between the nodes, we have edges. That's not an E. There we go, edges. And in this world of graph theory, you can really get into, well, let's see, if I count how many nodes there are on this envelope. 1, 2, 3, here's a node, here's a node, here's a node. It's wherever these vertices actually meet. So I have some vertices meeting, and I count 1, 2, 3, 4, 5, 6 nodes. Okay, so I have 6 nodes. And you know, this is now the math person coming in. This isn't the can I draw an art person coming in. In the 6 nodes, I see one node has 2 edges. So one node has 2 edges. I have 1, 2, 3, 4 nodes with 3 edges. You know, 1, 2, and 3. Well, wait, 1, 2, 3, 4. Excuse me. I counted that wrong. 1, 2, 3, 4. I only have 2 with 3 edges. And I have 3 with 4 edges. Is that correct? I see a yes from Matthew. So in the world of graph theory, you start looking at the number of nodes, and then you look at the number of edges. And as long as you have an even number of odd edges, you should be able to draw it without lifting your pencil. You should be able to do it in one continuous movement. There's a world famous problem called the Bridges of Konigsberg over here on the left. And it was drawing the bridges over these rivers. And can you make a trip starting at one spot, going over, crossing a bridge, then another bridge, and cross and cross. And you know, I'm not going to get into it in depth, but in the world of graph theory, you know, this was one of those that had to be proven. And if you look at this one down here, you know, they're throwing it on a graph. And if I had to make a graph out of it, how would I do it? You know, well, 1, 2, and 4 all go to the same place. So if I'm over here drawing it, you know, I have that, and then I have that one bridge coming over to that land, 2 and 4. I'll put this up on my screen in a minute. And over here, I have 4, and then I have bridge, you know, bridge number 7. I'll show you this in a minute. And then I see bridge 5 and 6 are coming here. Here comes 5, and here comes 6. And 1, 2, 3, 5, and 6 all go to the same spot. 1, 2, Here's 3, 5, and 6. So now if I stop sharing, I've taken the Bridges of Konigsberg problem and I turned it into graph theory, where each of the land was an actual node or vertice, and each of the bridges was. So now I look and I have 1, 2, 1, 2, 3. So there's a 3-noder, or 3 edges, excuse me, a node with 3 edges. Here's a node with 1, 2, 3, 4, 5 edges. Here's a node with 3 edges. So that's 2 of those. And here's a node with 3 edges. And it comes down to, like I said before, in the world of graph theory, do I have an even number of of nodes with odd edges? And so, no, we can't traverse this without lifting our pencil. So you can really, really get into the math part of this. And there's a lot of undefined things in the math world working with these, trying to prove formulas. What works for this case, this case, this case, this case, but then it starts getting so big you just don't know if it'll work or not. So we're going to take a brief look, a brief introduction of graphs and digraphs. Now, these are graphs, as I mentioned, but a lot of work we're going to do is with this thing called a digraph. So coming to my notes, digraph. It's, first of all, directed graph. It's not the same as the tree, because when I was showing you that envelope, you could have started anywhere you wanted in that envelope and basically traversed it from one node to the next to the next. So it's going to be a little bit different than a tree. And it's possible that not everything's connected. You know, look at the example I have down here below. Okay. Now, a digraph is different than a graph because it has arrows pointing from 1 to 2. So now I have a specific direction I can go instead of just having a regular graph that gives me all the options. And the digraph is the one we're going to use to start looking at possibly programming concepts of what's going on. So a digraph consists of a finite set of elements called vertices or edges, or excuse me, vertices or nodes, and then we have our edges or our directed arcs that will connect them. All right, so good. Still don't know how this ties into computer science, but you know, we're going to take a look in a minute. Does this tie into what we've been doing? Can I represent this with a matrix? Can I represent this with, oh boy, could I represent this with a linked list? Well, let me ask you this. If I took a look at node 4, how many directed edges, directed arcs could come out of 4? Kind of a trick question. Does anybody have an answer? I'll wait.
Can you
How
repeat the
many?
question one more time?
Yeah. How many edges could come in to 4? Well, I see one coming from 1, so that's at least 1.
2.
How many possible edges could come into 4?
5.
I hear 5. Trick question. Take a look at number 3. How many possible ones could come into 3?
3.
Yeah. No, 6. Because 3 could, 1, 2, 6, 5, 4 could all have arrows going to 3, but 3 could also loop around to itself. So this is me stuck in the airport in Fort Lauderdale or Fort Myers, and I'm trying to get home to 3. How many different ways could I get there? Well, I could go from 1 to 2 to 3. I could go from 1 to 4 to 3. I could go from 1 to 4 to 2 to 3. I go from 1 to 4 to 2. Uh-oh, this one's canceled. Back to 4. Now I have a flight to 3. Lots of different ways to get there. I could be at 3 and I could go out on the terminal and my plane could sit there and it could go right back into the terminal like it did on Sunday. So flying from city to city is a way to start the basics of a directed graph. You know, this city flights go from here to there, and so on and so on. And one of the big things that comes out of this is if I'm at city 1, what's my shortest route to get to city 3? 1 to 2 to 3, or else 1 to 4 to 3. You know, Florida to Charlotte to Harrisburg, or Florida to Chicago to Harrisburg. Well, in the winter, we don't want to go to Chicago. So we, you know, there's different, so just tying it into one thing. So yeah, there's lots of application. The biggest one is the shortest route, and that's the tale of the traveling salesman. We'll take a look at that on Thursday. Some of these are weighted. You know, would I want to go by a certain airline from 1 to 2 to 3 at a certain price, or 1 to 4 to 3? Different reasons to take different paths. Sometimes so-and-so will now start flying from 5 to 4. So we can always start thinking about this. And yeah, now all of a sudden I'm going back to my programming. What if I want to insert a node? What if I want to insert edges? You know, what if I want to build a new airport? What if I want to have different planes now flying to different airports? So, oh boy, this could get really, really kind of big, and so on. So some operations that are going on, you can see down at the bottom. How do I construct something like this? You know, what do I want to do? How do I see if it's empty? How do I destroy the whole thing? Insert a node, insert an edge, delete a node, delete an edge. Traverse through is a big thing. All right, some basic ideas behind graphs and diagrams. All right, so let's see what we can do. I already scribbled some stuff down, grabbing an eraser, and I'm going to leave one thing up here. Let me erase some of this. Duh, I don't have to erase it. I'm smart enough to get a whole new piece of paper. Come here, get over here. Okay, so let's start with something that's called an adjacency matrix representation. So I have a couple of nodes, A, B, C, D, E. I have a couple of arcs inside of here. I see one goes to 2, one goes to 3, one goes to 5. D goes to itself. A couple of others in there. So when I read the title, Adjacency Matrix Representation, I'm going to take this bad boy and I'm going to represent him by way of a matrix. Well, I dodge bullets every time I see a matrix. You can't see me doing it. All right, so how do I do it? Well, quick solution here is I'm going to draw 1 through 5, 1 through 5. I am going to say, does 1 go to 1? The answer is no. Does 1 fly to 2? The answer is yes. Does 1 fly to 3? The answer is yes. Does 1 fly to 4? No, and yes. So I can now start to take this into my computer world, and by storing all this information in my 2 by 2 matrix, I start to see a way that I can handle this information programming wise. Does 5 go to anybody? If I'm in city 5, I'm telling somebody they need to rent a car because we're not flying out to anywhere. And if I look at the graph, I can see 5 doesn't fly anywhere. Same respect, you know, so I could put from and to if I wanted to give these some labels. Now, here's what becomes interesting. I think it's fun, interesting. This records all of the 1 paths. If I go from 1 to 2, there's one way to do it, and I know I can do it. Okay, so not only does this signify that I can do it, it says, yeah, there's one way to get from 1 to 2. What I'm now going to do is take this matrix, I'm going to multiply it by itself. This is kind of cool. If you remember how to multiply matrices, row 1 by column 1, row 1 by column 2. Row 1, column 1 will then get stored in row 1, column 1. Row 1 by column 2 gets stored in column 2. Math nerds love our matrices. Just can't find a whole lot of uses for them sometimes. So what do I have? I have 0, 1, 1, 0, 1. 0, 0, 1, 0, 0, 0, 0. Oh, where am I at row 3? This should be a 1. Get the pencil out. Somebody needs to tell me to get the pencil out. 0, 1, 0, 1, 0. 1, 2, 3, 1, 0, and all zeros. Now I want to take that and I want to multiply it by itself. 0, 1, 1, 0, 1. 0, 0, 1, 0, 0. And I'm going to get a resulting matrix. When I take row 1 times column 1, I take the first element in row 1 times the first element in column 1, add them together, and I get a 0. Then I take the second element in row 1 times 0, the third times 0. This isn't going to be a lot of fun. The fourth times 0 and the fifth times 0. I just took row 1 times column 1. I add them together and I get a 0. Row 1 times column 2. 0 times 1 is 0. 1 times 0 is 0. 1 times 1 is 1. 0 times 0 and another 0. So row 1 times column 2 goes in row 1, column 2.
Wait, isn't that a 1?
Yes, it is. I wanted to see if anybody's paying attention. Now my calculator nerds are going, I can do this on my TI-84 in no time at all. That's fine with me. That's fine with me. I'm looking for the answer here. Row 1 times column 3 is going to be a 1. Row 1 times column 4 is going to be a 1. And row 1 times column 5 is a big old 0. Some of you quick math people, rocket math. Rocket math. Yeah, that didn't sell, so he had to change it to Rocket Man. Now I'm going to do row 2 times each of these columns. I'm coming up with a 0, a 1, a 0, a 1, and a 0. Somebody will let me know if that's wrong. I'm starting on row 3. I get 0, 0, 1, 1, 0. Row 4 times column 1, column 2, column 3. I get the ever popular 0, 0, 0, 1, 0. And the last row should be easy. Somebody can say, yeah, so what? Well, let's see what happens here. This is row 1, column 2.
You
That
ever
says,
get it-
yeah, did I
you
mess
ever
up?
get like a 2?
Did I ever get a 2?
Can you possibly get a 2 ever?
You can get a lot if you really wanted to. The more edges that are drawn up here, the higher the numbers will be. But this guy right now, this is A, this is B. Over here, it says to go from A to B by 2 steps, there's one way to do it. And if I look up, I can go from A to C to B. So this tells me paths of length 2. When I drew this representation up here, it was paths of length 1. So when I multiply paths of length 1 times paths of length 2, pow, it comes out awesome. This is C, this is D, B, C, D. Here we go. From D to D, not only can I get there, I can get there one way by 2 paths from D to D. Just keeps looping around. So yeah, the question of should we have had more arcs up here? And if we did, we'd have less zeros, which would give us some higher numbers here. Now, what's the problem with this? Well, we have a lot of zeros. We have a lot of zeros. Could we add new cities? You know, I'm saying they're cities. What number would the next city be? 6? So I'd have to put 6 and 6. Could I add new edges? Yeah. Does 1 now go to 6? Yep. Does 6 now go somewhere? So I could put new numbers here for 6. All of a sudden we might say, hey, wait, 3 now flies to 1. I could change that. So there's ways to go in computer science wise and start to do some preliminary work in the matrices. Maybe it's not a bad way to do it. Think of all the properties, all the functions that might apply here. Okay. So that was, yeah, doing it by matrices. All of a sudden, 2-dimensional matrices came into play. Let's take a look at second way to represent it. Same kind of structure as before. All of a sudden, you see the word chaining, and hopefully some of you are excited. And you know, all right, let's do this with arrays of linked list. And the first one, you know, I could call it array sub 1. I could call it array sub 0 if I want, but I can do the adjacency list, linked list, get it? Adjacency, the last one was matrix, because we use matrices, adjacency list, because we're using linked list representation. But in order to use linked lists, I'm going to bring in the idea of chaining. So can I get from here to there? Another way to store all of the information that might be needed for this. Adjacency list. I like it. If I throw this up, here's another one, right? I have all of this nice little diagram. Are you able to find the adjacency matrix? Yeah, we could draw that up. We'd have A, B, C, D, E vertically. Then we would have A, B, C, D, E horizontally. And we could make the matrix and draw up all of the numbers. I could say, can you get from A to D? You would be able to say yes. Could you get from A to D by way of 2 paths? And what would your answer be this time? I wanted to get from A to D by way of 2 paths. What's your answer?
Yes.
Yes. How many times?
2 times.
2 times. Very good. A to C to D or A to D to D. So now in that matrix where I squared the original one, I'd start to see some numbers that include a 2. What if I took the 1 path and multiplied it by a 2 path? Well, yeah, the resulting matrix would be a 3 path. Like, can I get from A to E by way of 3 paths?
Yes.
Yeah, I think I can go A to C, that's 1, to D, that's 2, to E, that's 3. So that matrix would show that representation. And then, of course, the adjacency list representation, we would have the first element in the array pointing, which would be A. A looks like it goes to B, to C, to D, and to E, almost everywhere. Just doesn't go to itself. All right, questions? Now, what if I said I'd like to, we talked a moment ago about inserting. We talked about deleting, inserting edges, deleting edges, inserting nodes, deleting nodes. What? Oh, look at that. That's a crazy one down there, isn't it? That's a good one. A cat, a dog, a bear, a rat, a horse, a zebra. Don't know what those lines mean, but that's something different. Different than just letters A. We have a bunch more going on there. Okay, so my question, how am I going to be able to traverse through some of these crazy things? Well, we're going to start with a way to traverse through a diagraph. And I'm going to take a diagraph in a moment down here. I have a big diagraph. And I'm going to start by talking about one of 2 methods to search through a graph. Now, we look at a tree and we know we're going to start at A. We're going to start at A just because it's set up as a root. And when we look at it in a moment for digraphs, we're going to have a starting point as well. A depth first search. When I see depth, I think of a depth charge. And when they used to roll the depth charges off the destroyers, they'd roll down, splash in the water, and they would just keep going straight down, either explode when it hit something or when it got to a certain pressure, I guess. But I'm going to keep that idea and depth first search. So here's the basic concept behind a depth first search. I'm going to start at A. I'm going to go as far as I can. I can go from A to B to E. A goes to B, it goes to E. Okay, if I start to back up, right, because I can't go any farther, I start backing, can I go farther? Oh yeah, I can go to F, I can go to H. Can't go any farther, I go back up. Can I go farther? Yeah, I can go to C. Can't go any farther, I go back up. I get to actually hit D and G. So if I started A, I could hit all of these. So keep that concept of depth first searching. Go as far as I can, then start to work my way back. But any chance I can get, I will go far again. So now I'm going to start with this graph. I want to do a depth first search. Where should I start? Somebody be creative. Pick a starting point, any point. Bueller.
G.
G. You can't see it, so that's not doing you much good. Well, come on now. Why don't I just tilt the camera? There we go. G. Let's see. If I'm at G, where can I go? What are my options? From G, I can go to B. From B, I can go to F. From F, I can go to G, but I know I can get there. I can go to I. I can go to H. I work my way back up. Nothing new from I, nothing new from F, nothing new from B. I go back to G. Let's see, I used the option B. Oh, I can also go to C. Can I keep going? I can go to D. I can hit H, which I've already hit. So by starting in G, these are all the letters I can visit. What if I had said I? I can only go to H. What about A? That's the one you all want to do because it comes first. Go ahead, tear up A, see where you can get. Is there one right answer? No, there's multiple answers. Because just because they're alphabetical doesn't mean we have to go that way. I could start at E, from A to E to H. Backtrack, backtrack. A to D to H, no. A to D to C, oh yeah. C goes to B. I'm going to keep going to F, to I, to H. So if I'm doing a traversal, every time I go to add something new, I'd have to check to see what's what's already been visited. I go back to F. At F, I could also go to G. G goes to C, got it. G goes to B, got it. So I'm backing up from F to B. B goes to F, and that's it. I back up to C. So all of a sudden, I'm starting to list these, and I'm getting a pattern of going backwards. C, I come to C. C goes to D, got it. Back up D, come back to D. D goes to C, got it. D goes to H, got it. Back up to H. I don't know how I got this crazy order. H ran out, E ran out, and A. 2, 4, 6, 8, 9. There's 9 up here. I froze up for a second. Yeah, am I back?
Sounds like it.
I'm back. Okay. You know what I almost said? I almost said, hello, hello, are you still there? But I know some of you have C string nightmares, and I don't want to bring that back up again. Questions about depth first searching. Ba-da-ba-ba-ba. Searching number 2. This one's called breadth first. So instead of going deep, I'm going to go wide. And I'm also thinking, if I had to program this, how would I do it as I rolled along? Breadth first. I'm going to start with A. Where all does A go to? Good, thanks. Participation sport, it is not. A goes to B. A goes to C. A goes to D. Y'all would agree to that, right? So we're going to keep an eye on these 3 as special because I know they are one path away. I'm only one path away. No. So now I'm going to go back to B. In my programming world, I'm keeping an eye on this. I'm going to go back to B and say, where does B go to? It goes to E and it goes to F. Check, done. C, where does C go? Nowhere. Where does D go? it goes to G. These three are a special group. Would you agree? They're a special group in that they are two edges away from a path of length 2 from A to here. So now the next group, anything else I put as I check E for breadth, F and G for breadth, are going to be 3 away. So if I go to E, there's nothing. If I go to F, there's H. If I go to G, there's nothing. So H is its own special group. Now I check H, it goes to nothing. So from A, these are all 1 path away. These are all 2 paths away. And this one is 3 paths away, 3 edges away. All right, similar to what we had with the last one. There we go. Can you do a breadth search on this? Can you do a breadth search on this? That's the one nice thing about this is it doesn't take me 3 minutes to put it on the board. Alex, did you ever show up? Oh, you did. So somebody's still missing. Somebody left early. So if Alex is here, we should have 15, but somebody left. You keep working on that. I'm going to figure out who left. Oh, I know who left.
How do you do this breadth first?
Okay, so I'm going to take a look at what I have here. Hold on 1 second. I need to put my book down. Where can A go?
To B,
It can go to B. Where else can A go?
D, and E.
B and E. Okay, so now I'm done with A. I'm going to back up to B. And I also am going to clarify these as 1 path away. I'm at E. Where can E go?
H,
I'm sorry. I meant to say B. Let's start with B. Do them in order. Where can B go?
F,
To F? Any place else?
no,
No. Where is it D can go?
H and C,
Yep. C and H. Where can the E go?
H,
To H, and we already have H, right? Good. So now I know these are 2 paths away. Let's see what they connect to. Does F connect to anything that I haven't already connected to? F
G
goes
and I.
to, F goes to G, and F goes to I. So I checked F. C goes where?
D,
C goes to B, but I already have B.
nowhere then.
H goes any place unique?
No,
Nope, so that's done. Now, from G and I, anything that connects onto this would be 1, 2, 3, 4 paths away. Does G connect to anything wait a minute, 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, 4, 6, 8, 9. Can I exit early?
yes,
Yeah, because I know I've hit all 9. So instead of continuing at this point, I might go, stop. Okay. So that's called a breadth or going wide. The book, don't look at, because the book has the same one, and it has errors. So as we said a moment ago, we have A, A goes to B, D, and E, right? It's a distance 1. So these are now all one path away. It's a good representation. Here, you know, I is 3 paths away. We have our 3s. We have problem is this graph is actually wrong. For some reason, they changed some of this to 2. But I have so much scribble on it, you probably can't read it. So here's what the traversal was. From A, we just said we can go to B, D, and E. So from A, don't look at any of this. From A, I can get to B, I can get to C, and I can get to E. It's kind of a confusing chart there for a while. So A, right here's A, it can get to B, to D, and to E. Capiche? B can now get to F. So this is a 2. That was my first letter up here. So that B, D can get to C and H. So that's why this becomes a 2, and this now becomes a 2. And E, my last one that was one path away, has no new. So I leave these alone. So from A to B, path of length 1, to C, path of length 2. So this is just counting sort of like we were doing without actually writing it down. So A went to B, D, and E. Since then, I now have F, C, and H. So where does F go? If it's any place new, it becomes a 3. F can go to G and to I. Where can C go? It becomes, you know, it would be a new 3, but we don't have any, nor H. But for some reason, this column got changed to 1s, and it didn't really need to be changed to 1s. Questions? Yeah, there's information in the book about algorithm writing and coding, but y'all know we just don't have class time to do it. So let's do a small one. A, B, C, and D. A to B, B to C, C to D, D to B. Okay, so here's an arrow for this one. Here's an arrow for this one. All right, what did we cover today? Adjacency matrix. Path 1 and path 2. The next thing we did was adjacency list, short for list link. And then finally, the last 2 were depth and breadth. Depth from, pick a letter.
D.
D. Breadth from, pick a letter.
A.
A. Put it all together. That's a 1. Number of edges is 6. Number inside of here is 6. Want to get paths of length 2. Multiply it by itself. Did I mess up? I got a thumbs up. So if I wanted to go from D to A, there's one way of doing it of length 2 paths, D to B to A. A to A, I can go from A to B back to A. Because we always check our work, right?
Yeah.
Yeah, good. Thanks, Peter. Depth, D. Depth charge, go as far as you can. And then work your way back. D to B to A to C.
To C.
And my count just went off. Ding, 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 ding. I don't have to go anymore because I equaled the number of nodes. But otherwise, I'd go back up to A goes to B, nowhere else. I'd go back to B goes to C, which I've been to. B goes to A, which I've been to, back up to D. The breadth search, again, gives us a whole lot more information because it lets us know paths of length 2 and paths of, but not completely the same as here. A goes to pick one, goes 2 different places. Where would you like to pick?
C.
A B? Does A go anywhere else?
C.
Yep. Okay,
D.
so I took care of it. A does not go to D. So now I back up.
Oh, wait.
Yeah.
Never
Now I
mind.
start with B. Does B go anywhere else? B goes to C, and that's it.
Mm-hmm.
So then I go to C, because this was done, this one's done. I go to C. Does C go to anywhere else?
Goes to D.
D, right? Now I'm at D. Does D go any place unique? And the answer is no. So A, B, C, D. Again, the bigger this would be, more options you have. You know, even here, I could have gone A to C first, and then from C, I could have gone to D, and then D would actually go to B. So that would have been another example of doing it. So there could have been a couple of different lines. Yes, under the IR link. Sorry, that's something else. All right, questions? No programming today, all information. Hopefully you got the concepts of what we were talking about. Hearing no questions, I will see you on Thursday.
Will this be on the test?
Yep.
Okay.
Anything else?
Seems pretty easy.
Good.